It's a great pleasure. It's a great pleasure to be able to talk to you. I really enjoyed the conference so far. My job usually at this stage is to try and summarize the cross-cutting themes and celebrate the diversity of the things that we've been enjoying over the past couple of days. But Tim asked me to be more self-indulgent and reflect upon things that me and my colleagues have been focusing on in the past year. So what I want to do is um, just briefly rehearse some of the things that we've been focusing on, and I'm going to try to pick up on some of the questions and the intriguing issues that you've encountered over the past couple of days as I go. But there were so many of them, I'm going to forget, I'm sure, most of them. So I've noticed that Tim has given me an hour and a half, which seems a little bit luxurious. So what I imagine will happen is I'll talk for, I would hope, about 40 plus minutes, um, answer questions, and then at Tim's discretion, then segue into a more general discussion, an open discussion of the emerging themes, the retrospective on the workshop itself. So I said it's self-indulgent. It's not that self-indulgent. So what I'm going to be talking about are themes and ambitions that have been worked up with colleagues from a number of spheres. And in fact, most of my colleagues are actually sitting in the audience, primarily from UCL and Versus, with interest from the Active Inference Institute. And some of this work has been motivated by a commitment to contributing to IEEE standards for the next kind of message passing protocols on the web, as represented by the Spatial Web Foundation. So I've sort of identified 5 themes. The most generic theme is trying to develop an expressive and universal generative model for discrete state spaces. That model can be thought of as a generalization or a more complete kind of partially observed Markov decision process, with a special emphasis on the role of paths and how paths may or may not be controllable, the hierarchical structure and what that means in terms of separation of temporal scales, and how that speaks to what Bert was talking about in terms of reactive message passing. The specifics of what this model brings to the table, I'm going to cover in terms of um, developments in active inference, specifically what is afforded by having an explicit representation of paths and the notion of inductive inference, or putting inductive inference into active inference, talking about generalizations of active learning, in the sense that active learning can be equipped with a very special meaning in the context of active inference if we look at learning the updating of model parameters as an action. And if it is an action, then it succumbs to the same principles as any other action, namely to maximize expected free energy of actions pertaining to the parameters. And we'll see what that means. You already know what it means because you've been talking about it, but it's nice to unpack it and relate it to established ideas, and illustrate active learning in the context of federated inference and belief sharing. And then finally, active selection. Again, the same notion of thinking about structure learning, Bayesian model comparison as an active process of comparing one model with another model, and again, leveraging the notion that every action, every move we make, including the way that we update our models, can be expressed as a process of minimizing expected free energy. And I'll illustrate that in the context of disentanglement. So that's the idea. Start at the beginning, the nature of things and how they behave. I've just summarized that here.
Sorry, Karl, can you maybe go to presentation mode?
And then my apologies. Yes.
And we can see your screen a bit better. Thanks.
Yes. Thank you. Is that, yeah, that should work, yeah? So the nature of things in the FEP, I've just tried to summarize the first principles account here in terms of a influence diagram or a sparsely coupled dynamical architecture that underwrites the free energy principle, and we've seen many times in different guises throughout the workshop. And just summarizing action and perception as the minimization of free energy with respect to action, and the optimization of the internal states representing external states, minimizing a generalized free energy that subsumed the expected free energy that has the normal interpretations in terms of expected information gain and expected utility or prior preferences. So that's the idea. It inherits from Markov blankets a la Pearl, but probably more conceptually from the notion of Schrödinger in terms of a spatial boundary and the importance that that separation plays in understanding self-organization of things in general. I introduced this because I had to examine a PhD thesis earlier this week by Sergio Rubin. And he wrote this, which I didn't, well, if I did know, I'd forgotten, but I thought it was really interesting. So after he introduces the notion of a spatial boundary, introduces the notion, one of the tenets of his account is that living systems remain organized because they feed upon negative entropy. And what I repeat, I'd forgotten or didn't know, is that in the second edition of What is Life, Schrödinger states, if I had been catering for them, namely physicists alone, I should have let the discussion turn on free energy instead. It is the more familiar notion in this context, but this seems a highly technical term, or this highly technical term seems linguistically too near to energy for making the average reader alive to the contrast between the two things. So it's a real shame that he didn't use free energy, because that would have made certainly our lives easier and possibly Richard Feynman's. So back to the Markov blanket. Just to demystify that for our friends from outside the Active Inference Institute, it's just a specification of the ports or the inputs and outputs to a system, where we are focusing on the internal organization that mediates the inputs and the outputs of the action perception cycle. And as we have covered from many perspectives, this can be characterized as message passing on a factor graph, and that's a theme that I'm going to develop. But of course, for every given factor graph, there is a graphical generative model and vice versa. So what kind of model have we been looking at for the past year? Effectively, we've been looking at a generalization of Markov decision processes that foreground the role of dynamics or control variables, or more generally paths, so that the transition dynamics depend upon a particular path. But of course, in the context of active inference and control, the paths themselves have a dynamics. And of course, the path, the next control variable, could either depend upon the previous control variable, say if I couldn't control it, or if I can control it, say I have some prior preferences that underwrite the expected free energy, then the path will change to the path that has the path of least action, or the path integral of the expected free energy, denoted by G here for each given path K. So C takes on a new role here as dynamics on things that are controllable, things that I can force in terms of changing their dynamics or their velocity, encoded by B. And then we have the normal Dirichlet parameterization for discrete state space models, leading to this graphical model here that has a temporal depth simply because we're paying careful attention to the dynamics among states, and in this instance, the dynamics among or over paths here with their initial conditions and the usual likelihood mapping. To make it completely general, of course, we need to equip it with hierarchical depth. And this is interesting because it brings to the table the notion that a state at one level basically entails a trajectory, a path, or a narrative at the lower level, say a spatial temporal receptive field, for example. And finally, of course, we've also heard about the importance of the mean field approximation and factorization, within any level and all levels of a hierarchical generative model, both in terms of the paths and in terms of the hidden states. So we have three characteristic kinds of depth to these deep generative models: temporal, hierarchical, and factorial. And that hierarchical structure has, I think, an interesting interpretation in relation to the temporal depth, because by construction, and indeed it's difficult to imagine how else you would construct it, what one is inducing with this hierarchical structure is a separation of temporal scales, in the sense if a state at one level maps to a path that has some universal clock time associated with it at the lower level, then an instant at the higher level corresponds to a chunk of time at the lower level, or at least a sequence of discrete events at the lower level, which necessarily means that the deeper I move into my hierarchical generative model, the more I progress towards the center, things slow down. And I've tried to cartoon that here in terms of the updates over time that will proceed relatively slowly, or you encounter less changes as you get deeper into the model and more changes at the extremities or the periphery of the model, the external Markov blanket, as it were. So that's, I think, a useful theme, which I'll just briefly recapitulate in a couple of moments. But let's just look at the corresponding factor graph. Magnus is going to be very cross with me because this is an old slide that does not conform to the normal standards, but I'm sure he'll forgive me. So here's the equivalent factor graph with the random variables, the states and the paths on the edges, and the factors of the conditional probability distributions associated with these various tensors parameterized by Dirichlet parameters here. And then, given this generative model, it is a simple matter just to write the update rules. There's no wiggle room here. They all fall out of the kind of universal message passing scheme that Bert was talking about. This is in fact just based upon variational free energy, giving you in some instances a mixture of belief propagation and variational message passing. I won't bother going through them, but other than to note, they rest upon a very small number of operators, which may be important from a computer science point of view. Basically, tensor operators, some product operators, and a couple of nonlinearities. And in fact, I just listed all the nonlinearities you would need here. Just a handful of nonlinearities, nonlinear morphisms, and tensor sum product operators, and that's it. This should, in principle, be applicable to any given generative model you had in mind in discrete state space, and would thereby allow you to build generative models if we have the right kind of software package. And we are moving towards those with things like RxInfer and Connors Pi MDP. One interesting twist here is just to think about, where is agency and where are agents, and is this hierarchical generative model a composition of different generative models, or is it one big generative model? Agency in this context inherits from planning, in the sense that if an agent has agency, she has to imagine the consequences of her actions. That is slightly distinct, I think, from controller's inference that we heard about in the last presentation, which you can get a long way with. But in active inference, we're moving to planning as inference with an explicit model of the future, where we score the quality of our plans in terms of the expected free energy. And we know the form of that from the pathological formulation from the free energy principle. And because we know the form, we know the dependencies or the messages that we'd need from other parts of the graph in order to constitute the expected free energy that underlies the selection of particular plans and implicit agency. And interestingly, it boils down to ABC. So I'm just making the sort of conceptual point, which may or may not be pragmatically useful, that an agent just is a collection of A, Bs, and Cs, but it can be embedded in a much deeper hierarchically structured graph. And I've illustrated the kind of graphs that we have in mind that may be a useful metaphor for, say, transactions, message passing on the graph, where the graph is now conceived of as, say, a web or an internet or um, um, Web3. So here's our little subgraph here with the agents here, and I've just squashed it here and then arranged it in this deep hierarchical form, just to give a visual impression of how one might conceive of federated inference and belief updating among multiple agents, where each agent is associated with a particular subgraph, such that certain agents inherit beliefs from other agents, even though they're actually looking at very different kinds of data or a different part of the world. And it's interesting to think about what would happen if you had lots of these deep graphs, in this instance, a factor graph, that were equipped with shared Markov blankets so that they could talk to each other and exchange. And we've heard some suggestions about this in terms of the implications for generalized artificial intelligence and belief sharing. From a purely physics perspective, an academic perspective, what should happen is that this kind of system will find its joint free energy, and that just means, from the point of view of the physics, it's going to evince a generalized synchrony. So everything is mutually predictable, in the sense that free energy just is surprise, and the average surprise is minimized when everything is mutually predictable. So we're looking at a kind of harmony that is a free energy minimizing solution that can have many readings. And here's a reading by my friend Takua in terms of Bayesian filtering that ensues from this kind of organization as a model of social intelligence and communication. So I'm going to now just run through 3 different levels that we've been focusing on in terms of active inference, learning, and selection. First of all, this focusing on one particular aspect of having paths at hand, or having a particular focus on paths, and the ability to now think about the way that we prescribe endpoints of these paths. So from the point of view of a physicist, you would normally describe a path in terms of the initial conditions in which you prepare a system and the endpoints. And then you're normally worried about the distribution over paths between the two. And indeed, that's where the variation free energy from Richard Feynman came from, the context of quantum electrodynamics. But from our point of view, it affords an interesting opportunity now to think about specifying the endpoints of paths as intentions or as intended goals. So I've sort of euphemistically described this in terms of, if I know that I'm here, then therefore I think I should go there, but only if I know where I am going. And we can derive a very simple but very effective kind of backwards induction from this sentiment, cartooned here in terms of, if I know all my allowable transitions in this context, and I know where I'm going to end up, then I know all the states as I back up in time that afford me access to the final state. And if I know that, I know which states to avoid. If I know which states to avoid, I can work out how close am I to my goal. And if I'm here at this distance from my goal in time, then I know where not to go next. And what we can do is we can just simply put that where not to go next into or add it to the expected free energy with a large negative number, and preclude directions of travel that I know preclude finally attaining my desired endpoint, or my intended endpoint. And this can be written down in terms of logical or inductive inference very, very efficiently, affording very, very deep planning, which is basically not choosing the best route to a desired endpoint, but really avoiding any states that preclude me actually ending up at that endpoint. I'm going to illustrate this kind of putting inductive constraints on active inference based upon the expected information gain and the expected utility, i.e. the expected free energies. And that hasn't changed. It's just that now we're constraining it with these inductive constraints. So the obvious one is getting to locations in some complicated maze. That we've already seen examples of this. So we start off with exploration using the expected free energy to maximize our information gain about the parameters, about the structure of the unknown world, usually leading to a deterministic and Bayes optimal, in the sense of optimal Bayesian design, interaction and navigation of my environment, covering all options, learning where I can and cannot go. And once I've done my effectively planning to learn, in the sense I am choosing those plans that have the greatest expected information gain. Why have I done that? Well, I can now learn to plan and find the best routes to my intended goals. And I've illustrated that here in terms of a couple of examples. Just to make 2 points. The first point is that there are 2 kinds of ways of specifying good paths. So the prior preferences, or the constraints, or the cost that we are used to that underwrites the expected free energy, or certainly the risk component of the expected free energy, can be regarded as basically constraints in terms of which parts of state space I do not occupy. So they put constraints on the path that are in play throughout the execution of that path. And this should be contrasted with the notion of an intended goal state indexed by H in the previous slide, which is just about the end point. Where do I halt? I'm illustrating that here. So under the same intended states here, I've got some strong constraints, prior preferences here for not transgressing black parts of this maze, and weak constraints. So just to illustrate the different kinds of route planning that one can evince from this combination, or putting inductive constraints on, in this instance, sophisticated inference, showing that there is an interplay between preferences described in terms of constraints and preferences described in terms of intentions. The other point I wanted to make, it's just interesting to note that the constraints we define in active inference for good reasons in outcome space. And those good reasons are simply, if you haven't yet learned your generative model, there is no state space to specify your goals. But if now we are sufficiently learned or developmentally mature, and we now have a generative model that frames and scaffolds a state space, we can now instantiate some instructional set or some intentions, or specify them from a higher level of a generative model in state space. So when I talk about inductive constraints on sophisticated inference, what I am implicitly saying is, within this learned generative model, I can now pick out certain latent states, hidden states that I want to end up in, and then leverage in this instance, the expected information gain, and pursue planning as inference under constraints to attain that particular goal. And this is an interesting distinction, which speaks to different kinds of sentient behavior. So you can imagine certain organisms, and indeed you can imagine thermostats, complying with the principles of controllers inference, and they can be very expressive thermostats, and you can simulate handwriting and walking and the like. But there now is a bright line between intentional behavior based upon the end point of a particular plan versus those based upon prior preferences, say a prior belief that I am walking or I am talking based upon some itinerant attractor or orbit in my generative model. We wanted to go back and revisit an illustration of free energy minimization in real neurons in vitro on glass that was published in Neuron last year, that it was claimed showed sentient behavior because they learned to play Pong. So Brett Kagan and colleagues in Australia basically put electrodes into a dish of neurons, supplied it or stimulated some electrodes, endowing this little in vitro neural network with information about the configuration of a game of Pong in a computer, but also had other electrodes picking up signals from the neurons that were capable of driving a paddle. And the fond hope was that this in vitro neural network, biological neural network, would learn to play Pong. Why? Well, because whenever it missed the ball, either any feedback was withheld or random feedback was supplied. So under the premise that the neural network was indeed self-organizing under the free energy principle, it wouldn't like random, unpredictable or surprising input, and therefore the only way to avoid that was to hit the ball back. And indeed, that's what it did. But the question is, to what degree could we find any evidence for intentional behavior? Did it intend to hit the ball, or was it just avoiding constraints implied by the preferences to avoid surprise, namely avoiding not hitting the ball? So we simulated this in vivo neural network in silico, in vitro neural network in silico, to see how quickly it would learn to play Pong, and compare it with the actual learning. And what we did, so initially, this is the first 500 exposures, and what you can see whenever the ball hits the bottom row, there's a sort of white noise, visual white noise, that the agent cannot predict and therefore will always be irreducibly surprising. But as time goes on, it does actually engage in a few rallies, where each rally entails a return of the ball for between 2 and 6 returns, very, very much like the real neural network. But then we continued the simulation and saw this kind of behavior under this inductive inference. So after about 500 exposures, this is a single epoch with just 500 data points, it starts to learn to gracefully play Pong. And in so doing, both minimize surprise in terms of avoiding this random input, but also in this instance, we actually told it at this point, hit the ball. These are particular states. Basically, you've got to be in contact with the ball because it had learned a suitable generative model illustrated by the likelihood mapping and the transition dynamics of the previous slide. So the neural networks never showed this behavior. They only got up to here. They never went there. So in our little jargon, they were sentient, but they were certainly not intentional. So you could say that they showed control as inference, but not planning as inference of this inductive sort or intentional sort. Good. Same kind of, exactly the same kind of learning and active inference deployed using the same code and the same inversion routines, but in this instance, in terms of the Tower of Hanoi program, a little game where you have to move these balls around on pillars to match a target configuration, and you can make it easy or difficult depending upon the number of moves to get to this arrangement. In this instance, there are 4 moves. It can learn the model in terms of the likelihood mapping and the allowable transitions among the different arrangements of these balls. And then we can switch on this kind of inductive inference, and in so doing, move. So this was sophisticated inference with just 1 step ahead. And it's not too bad, provided you give enough time to work towards the desired or the required arrangement of balls, and it can even solve problems up to 4 moves ahead on occasions. But as soon as you switch on this inductive inference, it gets 100% performance up to 9 moves ahead. And it's actually looking, in this instance, 64 moves ahead, but you could go much, much further into the future should you want to. Active learning in a particular context, and this context was established by thinking about how one could deploy this mechanics, this kind of Bayesian mechanics at scale, in terms of distributed cognition, ecosystems of intelligence, and implicitly federated inference. So my focus in this example is going to be on communication. How do you share beliefs among this federated and deep graphical structure, where agents are now subgraphs within this generative model of itself and the external Markov blanket. So the sort of to anthropomorphize this, I'm going to use a game hide and seek. So imagine there are 3 daughters or sisters playing hide and seek with their mother, and their mother's moving around trying to hide behind this and that. And the key thing is each of the sisters can only see a limited field of view. They can move their eyes around, but they can only see a limited horizon. And that horizon is distinct for each of the 3 sisters. And the idea is, can we see, or can we demonstrate the improvement in active inference, or the resolution of uncertainty and implicitly free energy, if this sister can hear her sisters? We equipped each of these agents with visual and auditory modalities. The visual modality had sort of high resolution foveal representations and low resolution peripheral vision, in addition to proprioception, where they were looking, and auditory, basically the sounds emitted by the other 2 and any given sister herself. A very simple generative model. I've just written out the first few lines of the MATLAB code describing the generative model for each of the 3 sisters. And then basically this is what happens at the top. This is what one particular agent would actually see through her various visual modalities. This is what was being presented, what the agent could see if she could see everywhere, and this is what the agent thinks she is seeing, noting that she can only actually see a very limited field of view at any one time. So our question was, what would happen if each sister broadcast their beliefs by uttering the location of the mother? So just saying a word that indicated their posterior belief about the location of the mother. And we simulated that simply by using precise and imprecise likelihood mappings to the auditory modality, and illustrating the results of being able to federate belief updating through communication, through articulation, through language, if you like. And I've done that here, we did that here, in terms of beliefs about location. So these are the beliefs of the 3 agents, with and without language or communication. The belief of the first agent is very precise because she could actually see her mother, but the other 2 agents couldn't. But what they can do is listen to what the first sister is saying, and resolve their uncertainty and form very precise beliefs, even though they've never seen mum at this stage. And we know that because when we remove this belief sharing, there is a lot of uncertainty about the location of the mother until the mother is actually visualized, because that's the only sensory evidence at hand to resolve uncertainty about mum's location, and one can score that in terms of the free energy differences. An interesting, so that's the setup that was motivated by an illustration of the utility of sharing beliefs amongst multiple agents. We had another agenda in mind, though, in setting up this particular game. The agenda was to demonstrate the importance of active learning. And I repeat, active learning has a very particular meaning in this instance. It's treating the notion of updating parameters of a generative model um, as an action. And if it's an action, the probability of doing it should be in proportion to a softmax function, the expected free energy of doing it relative to the expected free energy of not doing it. So now we introduce the notion of the expected free energy of a parameter that is acted upon through an update. And here's the update. We've heard about the importance of Hebbian or associative learning and active learning. In discrete state spaces, this is really trivial. It's just the pre and post synaptic activity or posterior probabilities multiplied together. And then that provides the update to the weight or the parameter of, in this instance, the likelihood mapping. And what we are saying is that we can either update or not, and score the probability of updating in terms of the differences in the expected free energy of that parameterization. So what is the expected free energy of the parameterization? And it's really simple. It's just the mutual information that is constrained by our constraints or by our preferences. And I think this is a really important observation, because what it says is that all learning at the end of the day is just in the service of maximizing the mutual information, not just on the likelihood mapping, but also on the transition dynamics and anything else that it constitutes the generative model. And of course, the ultimate of a mutual information, certainly in a discrete state space models, is where each column of a mapping or morphism has one in one element and zero everywhere. So it entails sparsity. It just means that the expected free energy of learning is just the drive towards a sparse, non-redundant, high mutual information, high efficiency mapping. I repeat, in this instance, a likelihood mapping or morphism. But it's not quite that simple. So there has to be a constraint, and we actually heard about explicitly the constraints on the sparsification or the maximization of mutual information. Those constraints in active inference are just supplied by the constraints that shape the kinds of states that you would expect to find this particular system in. So when one does that and works through the maths, you have a sort of very simple rule for updating. And what basically that does is it means that I'm only going to update if this is the right thing to do in terms of maximizing the marginal likelihood of my model, or the free energy of my model, and if the mutual information, constrained mutual information, is increased. If we now to go back to those three agents, those three sisters, and start off with a random likelihood mapping between their concepts, their posterior beliefs about hidden states, the state of the world, and their articulation, their belief sharing, so that they know no language. And then we just let them listen to each other under this particular kind of active learning, then what emerges is a high mutual information that is shared. It's shared because they're all jointly producing the same beliefs. So the only predictable exchanges that afford a high mutual information mapping are a shared acquisition of the same language. So the words, the articulations, producing the auditory sensations mean the same thing. And this is an emergent property. This language is an emergent property simply out of maximizing the expected free energy of the model parameters or the mutual information. That's cartooned here in terms of the convergence of parameters, the reduction of free energy, and due to inference and learning, and the slow increase over 400 to 500 exposures in terms of mutual information. And so finally, moving on to a similar idea, but in this instance, not in terms of updating the parameters, but actually updating the structure of the model itself. And what that leads to is the notion of active model selection, where we use something that's underwritten statistics for a model comparison for decades and decades, based loosely on a Savage-Dickey ratio. You may recognize this as its generalization in terms of Bayesian model reduction. And all we're doing here is saying that there's an act in play. And the act in play is, do we equip my generative model with another state, another factor, another level to any given hidden state? And answering that question by saying, well, what happens to the expected free energy, or what happens to the marginal likelihood, or the model evidence? And under the assumption that the two likelihoods, the two likelihoods are the same. No, I'm not under that assumption, but under the assumption that we have some particular priors about whether this new observation warrants or is likely or not, I can then evaluate the relative probability of two models and decide whether to update or not by comparing the model evidence for this new observation by comparing two models with and without an extra latent state or level to a latent state, a new path or a new factor of latent states, each equipped with, in the first instance, just one path identity matrix or stationary mapping and two levels to it. So I'm illustrating that in probably its simplest application here, which is just in a static context, just trying to classify or carve nature up to its joints in terms of identifying how many species are there if I was an ecologist or an evolutionary theorist, or in this instance, how many species of handwritten digits are there in terms of the style in which I can write any one particular digit. So all we're doing here is only updating our model by adding a new style for any given particular digit if this condition is met. And that's what's meant by active model selection. And we can control that with a species discovery prior. Plays the same kind of role as all the stick breaking processes and, say, Chinese restaurant processes that you would find in non-parametric Bayes, but a little bit simpler in this instance. And I can accumulate thousands and thousands of observations of handwritten digits here, the MNIST data set, and work out how many different styles there are. And once I've done that, I got two factors. One is the class, the number class, and the other one is the style, or the style class. And here I think there were 256 different ways of writing certain numbers. Other numbers, only about 50 ways of writing them. That was actually number one here. And doing that, you can, or having grown your model, this is a kind of Bayesian model expansion based upon this active selection, one can then look at the learned or the acquired or accumulated information geometry by looking at the sort of the information lengths approximated by KL divergences between different classes and different styles, and proceed in the normal way in terms of clustering, in this instance, different numbers. Finally, taking the same notion but now into dynamics, where now the way in which you grow the model, the way in which you deploy this active model selection, accommodating or making a decision in the face of any new bit of data, do I augment the model or not? And if I do augment model, how do I augment it? Do I add another state? Do I add another path to any given factor, or do I actually add a new factor? It transpires that you can simplify that and develop a kind of structure learning that depends upon the sequence in which you present data for a simulation for the agent to make a decision about whether to grow or expand the model or not, with a relatively simple curriculum. So I'll just summarize this um, in narrative form here. So if this is the very first thing I see, I'm going to create a likelihood mapping with a single state and populate it with initial Dirichlet counts, namely the concentration parameter of a symmetric Dirichlet distribution. And then for every other observation, I'm going to consider an additional state for the last factor, provided there's only one path, and that path is by design a stationary path, a path that you just remain in the same state. Otherwise, consider an additional path or factor, and if I'm putting a new factor in, then it's going to clearly have just two states with one stationary path, because the first state is the a state of the previous factors that is required to link different factors together. And when we use that kind of, it's almost structured teaching really, because you have to be very careful about the sequence in which you present the successive data points that are being assimilated. Not too careful, because it's exactly in the order that the dynamics of the real world would present it, but still you have to actually be careful when you're simulating this. We can now do structure learning of the kind that could be read as a very elemental disentanglement of sprites here, and yes, the sprites themselves are just summarized here. So in this particular example, the world could be the world could contain one of three different kinds of objects, and these objects could move around. Just to make things interesting, we actually equipped the agents with prior preferences for locating each of the three different kinds of sprites to different quadrants, following the work of colleagues Zaf and others, Kent. Crucially, the preferred locations of each of these objects were different. And I repeat, each object can move up or down or sideways or both. But the agent didn't know that. The agent was completely naive. In fact, the MDP structure, the Markov decision, or partially observed Markov decision process, was never actually specified by hand. It was automatically grown just by feeding it data that had been generated from a process that had already been learned. What it can do, or what it should do, is basically learn receptive fields for vertical and horizontal positions, and the map of preferred locations that will ultimately cause it to draw these sprites to the locations. And indeed it does, using this. So this is the learned, auto-assembled, self-created structure learning in terms of the likelihood mapping. It's all been concatenated for visualization, and the different transition dynamics for each of three factors. So it's learned there are three factors, and basically these three factors are things can move right and left, or they may not. Excuse me, they may not be moving, or they can be moving up and down, or not moving up and down. And there can be three kinds of things that are moving left and right, or up and down. And it's also learned the preference mappings here. This just scores the number of times each of these areas, each of these locations were revisited. I should say an important part of this kind of structure learning is after a time, the agent autodidactically makes moves to fill in the gaps, a bit like motor babbling, based upon those actions that maximize expected information gain about the parameters. So once it's got the structure in terms of the number of factors and paths within each factor, so number of factors here, number of levels for each factor, and the number of paths for each factor over the columns here. Once it's got the structure, then it can sample the world in a way to fill in the tensors on the basis of informed epistemic moves that are chosen on the basis of the expected free energy, or I repeat, the expected information gained about the parameters, and it learns exactly the right receptive fields and the likelihood mappings. And this is the final slide. It just illustrates the kind of learning that you get, and evinces something that we've seen at least twice, if not three, if not more times throughout the presentations during the workshop. This systematic progression from exploratory behavior to exploitative behavior. So this is the number of trials during this epistemic foraging, during this, if you like, motor babbling, that show that initially it requires, as one might guess, given this was a sort of 9 by 9 visual scene, it requires about 81 exposures to start to fill in all the important gaps here, during which time the expected information gain is very, very high for each of the three sprites here, with the evidence lower bound here going up and down during this exploratory phase. But after it's learned, and notice it's has very precise beliefs, it's very confident, just to pick up on one of the presentations, it's very confident. It has a low entropy distribution over policies, or over where to move the sprite on each time step during the exploration phase, because it knows what is epistemically has high epistemic affordance, and therefore makes very confident epistemic moves initially, and then as it becomes familiar, the expected information gain falls. It starts to lose some confidence in terms of the precisions, and settles down to a reward-based exploitative pattern of behavior, and just maintains the sprite over its preferred direction, and becomes bored, presumably. And that's it. That's a brief whirlwind tour of what me and my friends have been doing in the past year. I'll close with Einstein. Log evidence is basically simplicity plus accuracy. In other words, everything should be made as simple as possible, but not simpler. Just to sort of recapitulate that in terms of planning as inference and the expected free energy, the important thing is not to stop questioning. Curiosity has its own reason for existing. Indeed, I would argue that existence just is the expression of curiosity. So that just remains again for me to thank all my collaborators. Their affiliations are shown along the top here, and I repeat, most of you are in the audience anyway, so you know exactly who you are. I'd like to thank you for your attention, but just take this opportunity just to thank Tim and the organisers for this opportunity. I was touched that Tim was thanking me for attending. I thought that was quite incongruous yesterday, because I was really enjoying myself, sitting here admiring everything, having a cup of coffee and smoking with gay abandon. So thank you very much. I'll pass the chair back to Tim now.